Now we will discuss about various SQL statistics such as SQL ordered by elapsed time, CPU time, user I/O wait time, gets reads, physical reads, unoptimized, executions, parse calls, shareable memory, version count. SQL ordered by elapsed time lists SQL statements that have consumed the most elapsed time. SQL ordered by CPU time lists SQL statements that consume significant CPU time during its processing. SQL ordered by gets lists SQL statements that have a high number of logical reads while retrieving data from buffer. SQL ordered by reads lists SQL statements that have a high number of physical disk reads, counts database blocks read from the disk, not actual I/OS. SQL ordered by physical reads, unoptimized, lists SQL statements based on the number of I/O requests and not the number of blocks returned. SQL ordered by executions lists SQL statements based on executions and number of rows that were fetched. SQL ordered by parse calls lists SQL statements based on the number of parse calls. SQL ordered by shareable memory lists SQL statements based on the amount of shareable memory used. SQL ordered by version count lists SQL statements based on the number of versions generated for those statements. Complete list of SQL text lists SQL statements with complete text. The SQL ordered by elapsed time section of an Oracle AWR lists SQL statements that have consumed the most elapsed time during the specified snapshot interval. This information can help pinpoint long-running SQL queries that may be causing performance bottlenecks. It provides valuable insights into the CPU time, execution frequency, and the SQL module associated with each query. Identifying the top SQL queries allows us to correlate them with potentially slow or extended processes within the application. Additionally, the elapsed time is a key indicator for identifying multi-threaded SQL, including parallel DML/SQL or processes with multiple workers. When a SQL query is multi-threaded, its elapsed time will be significantly greater than the AWR duration or the observed clock time of the process/SQL. This aggregated elapsed time includes the cumulative time spent by all workers or parallel child processes associated with that query. Furthermore, it's essential to inspect the SQL_text section for PL/SQL calls. This inspection can help in recognizing instances where SQL queries are calling other SQL queries, which is crucial for understanding the flow and dependencies within the application. Elapsed time, this column represents the total elapsed time, in seconds, spent on executing each SQL statement during the snapshot interval. It includes both CPU time and wait time. Executions. The executions column indicates how many times each SQL statement was executed during the snapshot interval. Elapsed time per exec, this column shows the average elapsed time per execution of the SQL statement. It's calculated by dividing the total elapsed time by the number of executions. Percent total. The percent total column shows the percentage of the total elapsed time consumed by each SQL statement in relation to all the SQL statements listed in this section. Percent CPU. The percent CPU column indicates the percentage of CPU time consumed by each SQL statement in relation to the total elapsed time. Percent I/O. The percent I/O column represents the percentage of elapsed time that involved waiting for I/O operations. It indicates the I/O related performance impact. The SQL statements listed in this section are ordered by the total elapsed time, which indicates the most time-consuming SQL statements in the database during the specified time interval. Oracle elapsed_time metric equals CPU time plus user I/O wait time plus application wait time plus concurrency wait time plus cluster wait time plus PLSQL exec time plus Java exec time. The top SQL statement is executed frequently but is relatively lightweight per execution in terms of elapsed time. It is primarily CPU bound and experiences minimal I/O wait time. The second SQL statement, despite being executed only once, is extraordinarily time-consuming. It consumes both CPU and I/O resources, indicating potential performance issues. The extremely high elapsed time for the second SQL statement suggests a significant performance bottleneck. Further investigation and optimization may be necessary to improve its performance and reduce the elapsed time per execution. The SQL statement with SQL ID for W9WVDFWTCK1X and SQL module JDBC Thin client is the most time-consuming, with approximately 2,908.03 seconds of elapsed time, and it is executed 15,524 times. The high percentage of CPU time, e.g., 99.56%, for some statements suggests that these SQL statements are CPU-intensive. Some statements have a significant percentage of I/O time, e.g., 75.2%, indicating that they involve substantial I/O operations. The number of executions varies among the listed SQL statements. Some SQL statements have a very high elapsed time per execution, indicating they are relatively time-consuming per execution. The SQL statement with the highest elapsed time contributes to approximately 3.89% of the total elapsed time. Some SQL statements consume a significant percentage of CPU time during execution. Some SQL statements perform a notable amount of I/O operations. Monitoring and optimizing these high elapsed time SQL statements is important for improving overall database performance, especially if they are frequently executed. Further analysis and tuning may be required for specific SQL statements that have a disproportionate impact on the total elapsed time or resource consumption. Investigating these SQL statements and their resource consumption patterns can help identify opportunities for performance optimization and resource allocation. Overall, this section of the AWR report highlights the SQL statements that have the most significant impact on elapsed time and resource utilization within the database during the specified. SQL ordered by CPU time. The SQL ordered by CPU time section of an Oracle AWR lists SQL statements that have consumed the most CPU time during the specified snapshot interval. CPU time represents time spent on CPU and does not include time waiting for CPU. CPU time, this column represents the total CPU time, in seconds, consumed by each SQL statement during the snapshot interval. Executions, the executions column indicates how many times each SQL statement was executed during the snapshot interval. CPU per exec, this column shows the average CPU time per execution of the SQL statement, calculated by dividing the total CPU time by the number of executions. Percent total, the percent total column shows the percentage of the total CPU time consumed by each SQL statement in relation to all the SQL statements listed in this section. Elapsed time, this column represents the total elapsed time, in seconds, spent on executing each SQL statement, which includes both CPU time and wait time. Percent CPU, the percent CPU column indicates the percentage of CPU time consumed by each SQL statement in relation to the total elapsed time. Percent I/O, the percent I/O column represents the percentage of elapsed time that involved waiting for I/O operations, indicating the I/O related performance impact. The SQL statements listed in this section are ordered by the total CPU time, which indicates the most CPU-intensive SQL statements in the database during the specified time interval. The top SQL statement consumed the highest CPU time of 2,895.32 seconds, was executed 15,524 times, has an average of 0.19 seconds of CPU time per execution. An average of 0.19 seconds of CPU time per execution accounts for 7.77% of the total CPU time, had an elapsed time of 2,908.03 seconds, is primarily CPU-bound, with 99.56% of its elapsed time attributed to CPU usage, had negligible I/O wait time, 0%. The second SQL statement follows closely with a CPU time of 2,024.78 seconds, was executed only once, has an extremely high average of 2,024.78 seconds of CPU time per execution. Has an average of 0.19 seconds of CPU time per execution, accounts for 5.43% of the total CPU time, had an elapsed time of 2,033.39 seconds, also consumes a significant amount of CPU time, 99.58%, experienced a substantial I/O wait time, 0.23%. It consumes a substantial amount of CPU resources and has a considerable I/O wait time. The extremely high CPU time for the second SQL suggests a performance bottleneck. Some SQL statements have a very high percentage of CPU time, e.g., 99.56%, indicating that they are primarily CPU-bound. The SQL statement with SQL ID 6th and SQL module declare job binary underscore integer has a high Percentage of I/O time, e.g., 44.85%, suggesting that it involves significant I/O operations. The elapsed time column provides additional context, as it helps identify SQL statements that have high CPU time but might not necessarily have high overall execution time. Analyzing and optimizing SQL statements that consume a significant amount of CPU time is crucial for improving database performance, especially if they are frequently executed. To reduce high CPU usage, one needs to find its source within the database. The first thing to check is parsing, not only because this is a CPU-intensive activity, but also because high parsing means lack of cursor sharing, which makes diagnostics very difficult. Some expensive sorts that could be avoided, etc. CPU consumption in the host operating system can also be important for troubleshooting high CPU usage. AWR provides these numbers in the operating system statistics section. As busy and idle, the units are sent to seconds. SQL ordered by user I/O wait time. The SQL ordered by user I/O wait time section of an Oracle AWR report lists SQL statements that have experienced the highest user I/O wait times during the period. The I/O wait is an administrative wait class such as log files, while user I/O is an application wait class such as a database file, DBF. A database with no user SQL being run generates little or no I/O. Ultimately, all I/O generated by a database is directly or indirectly due to the nature and amount of user SQL being submitted for execution. This means that it is possible to limit the I/O requirements of a database by controlling the amount of I/O generated by individual SQL statements. This can be accomplished by tuning SQL statements so that their execution plans result in a minimum number of I/O operations. User I/O time, this column represents the total user I/O time, in seconds, incurred by each SQL statement during the snapshot interval. Executions, the executions column indicates how many times each SQL statement was executed during the snapshot interval. UIO per exec, this column shows the average user I/O time per execution of the SQL statement, calculated by dividing the total user I/O time by the number of executions. Percent total. The percent total column shows the percentage of the total user I/O time consumed by each SQL statement in relation to all the SQL statements listed in this section. Elapsed time, this column represents the total elapsed time, in seconds, spent on executing each SQL statement, which includes both user I/O wait time and CPU time. Percent CPU, the percent CPU column indicates the percentage of CPU time consumed by each SQL statement in relation to the total elapsed time. Percent I/O, the percent I/O column represents the percentage of elapsed time that involved user I/O wait time, indicating the I/O related performance impact. The SQL statements in this section are ranked by their total user I/O wait times. The listed SQL statements are executed only once but incur extremely high user I/O wait times, suggesting intensive I/O operations. These SQL statements are likely involved in data-intensive operations that rely heavily on disk I/O. Each SQL statement accounts for a significant portion of the total user I/O time, ranging from 1% to 4.89%. SQL statements have a very high percentage of user I/O time, e.g., 75.2%. Indicating that it is primarily I/O bound and involves significant disk read or write operations. Analyzing and optimizing SQL statements that consume a significant amount of user I/O time can help improve database performance, especially if they are frequently executed and involve heavy I/O operations. The following areas can be addressed. Tune SQL doing the most I/O, or logical reads. Even tuning SQL not doing DB file scattered read might lighten any general I/O congestion. Size the SGA buffer cache based on the advisors. Tune the schema, e.g. investigate if partitioning can reduce I/O. Look for objects that can be shrunk via online shrink, leveraging segment advisor, perhaps in conjunction with purging old data. Investigate the use of materialized views to save both online processing time and I/O in general, and possibly of offload processing to a remote DB. Result caching allows you to store the results of queries, query fragments, and function result sets. Investigate the advanced compression option to reduce the amount of I/O required. Cache specific objects into the SGA buffer cache.